Today's webinar is entitled How Deep Learning is Poised to Change Your Life Forever. Our presenter is alumnus Dr. Raymond Ptucha, the director of RIT's Machine Intelligence Laboratory. Dr. Ptucha holds 2 RIT degrees, a master's degree in imaging science and Ph.D. in computer science. He also holds a BS in computer science and a BS in electrical engineering from SUNY Buffalo. He currently serves as assistant professor in computer engineering in the Gleason College of Engineering, specializing in machine learning, computer vision, robotics, and embedded control. Prior to joining RIT's faculty ranks, Dr. Ptucha was a research scientist with Eastman Kodak Company for 20 years. He worked on computational imaging algorithms and has been awarded 31 U.S. patents with another 19 applications on file. In 2010, Dr. Ptucha was awarded a National Science Foundation Graduate Research Fellowship for his advanced studies at RIT. His Ph.D. research earned the 2014 Best RIT Doctoral Dissertation Award. Dr. Ptucha is a passionate supporter of STEM education and an active member of his local IEEE chapter. Dr. Ptucha, it is all yours.
Thank you very much, and good afternoon, everybody. Welcome. I'm going to be talking about some interesting changes in our technology, and in particular, I love new technology. This morning I was driving into work, and I'm thinking, boy, every day I do this 20 minutes driving to work, 25 minutes going back or so, depending upon traffic. Wouldn't it be awesome if I could just sit in the back seat of my car and have the car do the rest for me? And further, it's raining today. Wouldn't it be nice if the car can just pull up to my office door, let me out, and then go park itself? Similarly, as I sit here, as I have conversations with people, I'm a firm believer that in the future we'll have these ubiquitous devices with us at all times. For example, this particular device, it could be, let's call it an agent. I'll have a conversation with it when I'm done with this, and it'll tell me some of the good things, some of the bad things I said, some of the interesting comments from listeners, and so on. Perhaps I could have questions about a schedule, similar to the way you do an OK Google or a Siri. Further remind me of appointments, and perhaps I'll even share intimate secrets with this particular agent, things that I wouldn't even share with other personal humans, and it'll give me frank advice, and thus it may become one of my best friends in the future. Further, as devices affect our lifestyle, I can't wait till I wake up in the morning and my house somehow automatically monitors my health and lets me know if there's some problems just by, say, looking in the mirror. And simple tasks such as cutting the lawn all happen automatically without even me knowing or realizing it's going on. Now, as we talk about machine learning, first of all, machine learning would be the ability of machines to generalize, to think and behave, react, do things just like humans do. Now, this particular field of machine learning, and we're going to talk specifically about deep learning, which is one aspect of machine learning today, it's really transforming so many different aspects of life, from financial markets, international security. Really, it's making our lives so much better, and perhaps you will have a much better lifestyle than all other prior generations to us. Now, if we just take a look at the popularity of machine learning over the past couple of years, so this is people, Googling machine learning, and this is the popularity of Googling that particular keyword, machine learning, over the past 5 years or so. And you can see it's really gotten very popular with about a 4x increase in the past 5 years. Contrast that to something, to deep learning, which is what we're really going to talk about today. That was really an unknown word. Very, very few people Googled that 5 years ago, and so there's well over a 25 increase in the past 5 years on that. Further, if you take a look at Stanford University, which is the #1 most popular university other than RIT in the world, when you look at the popularity of their specific courses, they used to have a course on machine learning, which is their most popular course, and now that's finally been superseded. There's a course called CS231, which is a deep learning class, and its initial offering, there was 150 students. The second offering, it went to 350, and this spring it jumped to 750. And so this just shows you how interested students, people who are studying science and technology, are in this particular field. Now, I'd like to think that we're entering what we call the fourth industrial revolution, where the first industrial revolution was, say, in the late 1700s, started, say, in England with water and steam, and starting to, build machines which you could do things which typically humans would have been doing. And then in the early 1900s, with the discovery of electricity and feeding of electricity to plants and homes, the automation, Henry Ford, mass production, that would be what we call the second industrial revolution. And then in the 1950s, with the discovery of silicon and transistors, electronics, and manufacturing lines which are becoming more automated, each one of these industrial revolutions, our lifestyle got increasingly better. Now, I would like to think that starting about 10 or 15 years ago, we're just starting what we call the fourth industrial revolution, which I call the cyber-physical, where the boundaries between, biological, electronics, and humans is starting to get blurred. In other words, I talked about those examples of, some sort of agent which goes around with me and gives me advice, and I ask it questions. This is sort of like, wow, this is going to be a part of my life. Perhaps one day there'll be a chip which I plug into my brain, and maybe on that chip is the entire, Wikipedia of all information. Every time I look at somebody, it'll give me detailed information about who exactly that person is, how do I know them, their complete first name, last name, the names of their kids, any other detailed information. So maybe we could have richer conversations with people. Now, so I'd like to take a moment and talk about the point of singularity. Well, that's roughly defined as when computers become smarter than humans. And let's stop, but let's think first of all about humans, and in particular about evolution. Our ancestors, go back a couple of million years. Modern humans maybe only 200,000 years. And civilization, let's say 5,000 to 6,000 years, modern civilization. Well, we hear over and over again that over time our brains are getting bigger, humans are getting smarter. Well, if we take a look at evolution over the years, say over the past couple of thousand years, we have a timeline in blue over here over time showing that, yeah, our intelligence has been getting greater. So the y-axis would be the amount of intelligence, and the x-axis would be time, and we can see that intelligence is getting greater. But because this timeline is so long, for all intents and purposes, it's almost as if we can't tell as humans on planet Earth today that humans are getting slower. I mean, could you say that you're smarter than your parents or your grandparents? It's hardly noticeable. But, if we compare ourselves to maybe our ancestors from 100,000 years ago, yeah, we probably are smarter. Well, let's contrast that to the red over here, which is essentially computers or machines. Well, over time, there really were no machines, so they had, say, zero intelligence over time. But over the past, say, 50 years or so, that intelligence is starting to increase. And then in the past 10 or 15 years, it's been increasing even more. And now we're at the point where computers they're still not quite as smart as humans, but there's definitely a pattern here. We see how these computers are getting increasingly smarter. And so I'd say it's not if computers will get smarter than humans, it's a matter of when. So at some point in time, there'll be this crossover, which we call the point of singularity. Now, Ray Kurzweil, he's a futurist. And what he does is he makes predictions about science and technology. And in particular, in this particular chart, he's showing, over time on the x-axis versus computations per second per $1,000 on the y-axis, just how computers are getting smarter and smarter. And back in the 1990s, he made a prediction that, hey, by the year 2000, we'll have a single computer which is just as smart as an inkjet brain. And sure enough, that came true. Also back in the 1990s, he made a prediction that by the year 2010, there'll be a single computer which is just as smart as a single mouse brain. And that came true as well. The next prediction, which is the most interesting, was then he said, well, I will predict by the year 2029, there will be one single computer which will be just as smart as a human brain. Okay, remember, this is his prediction. This isn't truth or anything. This is what he's saying. Then he said, I'll tell you what, I'll even take it one step further than that. By the year 2049, there will be one single computer which is just as smart as, say, all our collective brains in this room and on the phone. And tell you what, let's even throw in everybody at RIT, all students, all faculty. We all put our collectively brains together. There'll be one computer which is just as smart as us. Something, check that. He's even a little bit more bullish on it. He'll say if you took every single human on planet Earth, if you took 8 billion brains and you put them all together and they were working on one single problem, we'll have one single computer which is just as smart as those 8 billion people working on that one problem. And he's predicting this will happen in the year 2049. Now, it's very interesting. So, I'm very jealous of a lot of my students because they're going to probably live to see a lot of things which I don't see, which, I'm so excited about. As we slowly see, as machines are getting smarter and smarter, eventually they'll match and then they'll surpass so many human capabilities. For example, today, let's say I'm driving down the highway, I'm with the wife and the kids in their back seat, and we're just, say we're on a vacation, we're driving, and one of the kids in the back says, hey, Dad, Mom, Dad, take a look. There's one of those really cool-looking cars with one of those spinny things on the top. That's one of those autonomous cars. Look, there's no driver in there. Everybody turns and says, wow, cool, that's awesome. Well, when they grow up and when they're my age, let's say now they're driving, and they have their own kids in the back seat. So their kids in the back seat, they'll be driving along the vacation, doing what kids do, probably picking on each other, what have you. And all of a sudden they say, hey, Mom and Dad, look out the window. There's one of those really cool cars. There's a human driving it. And everybody looks like astonished because humans don't drive cars anymore. I mean, humans, their reactions are slow. They get distracted. Maybe they drink and they drive. They can't see in all directions. They can't communicate with all objects all around them. So there's many different things that humans can't do which computers can.
So, Ray, let's see if we can get the brains on the webinar here to work on a question for you. We have our first poll question up. And remember, if you are in full screen mode, you'll need to return to the traditional screen to see the poll questions on the right-hand side. So we're asking for your views. What do you think? When will computers become as capable as human beings? If you want to take a moment or two, a couple moments, and answer that question, I think you can jump into the next slide.
Okay. Can I move this to the side?
That's not you.
It all just popped up. Okay, so now Andrew Ng, he's one of my heroes. Andrew Ng was a Stanford professor for many years, and eventually he went to Baidu, and he was a chief research scientist at Baidu, and now actually he even left there, and he's starting his own company back in Silicon Valley. But so he has this quote, AI is a new electricity. Just like electricity transformed the world as we know it in the 1900s, AI is transforming our lifestyle right now today. So if we take some popular companies like Google and Facebook and Apple and so on, they're just hiring herds of deep learning experts every single day. Baidu alone has over 1,300 deep learning engineers, and Google has well over 100 groups of deep learning engineers. This is the technology which is really transforming our lifestyle. Is there a way, can I see the results?
Yeah, I think we're just about finished.
Okay, so let's take a look at how some of you answered here.
Looks like most everyone is thinking closer than farther. More like 20 years. Some of you are into the 50-year range.
This is an interesting question because there really is no real answer to this particular question. I think keep in mind, we really don't know when this will happen, but we do know it will happen. Ray Kurzweil is probably the most bullish on this, but what I have here on the next slide is I'm showing some other futurists who make predictions about when this might happen. And we start up in the upper left-hand kernel with Ray Kurzweil himself. And so he's predicting in the year 2029. But if you take a look at some other popular people, for example, Robin Hanson, he's a very famous author on AI technologies, and he's saying this can take 1 to 400 centuries before this will happen. Rick Curie, he's the chief architect of IBM Watson. He was the guy who did the Jeopardy when it famously won against the human contenders. And he's even saying, I didn't want to make that prediction because there's so much that's going to happen between now and then that why are you asking me this silly question? Other famous folks, Nick Bostrom, he's thinking that it can happen in a couple of decades. Rodney Brooks, he's a very famous roboticist from MIT fame, and now he has several different startups he's done. And he's just saying, hey, all you guys who thinking this is going to happen, it's not. So save your breath. We'll never see it in our lifetimes. And then there's Gary Marcus. He's actually a psychology professor, and he's also a futurist, and he's thinking about 20 to 50 years. So for those of you who thought it would happen at any of those particular times, we can say, hey, you all got it right. All right, so let's take a look at some AI trends that are happening now. So first of all, supervised learning, which is perhaps the most popular type of artificial intelligence trend. This is where you actually train these computer models using ground truth exemplars. And these ground truth exemplars usually come from humans themselves. So the humans are actually manually training these particular models. Now, you hear lots of hype about AI. Some people are saying, Terminator is going to take over, and this, that, and the other thing. We're a long way away from that. As a matter of fact, there's a good rule of thumb you can apply. And you say anything that a human can do, say in less than 1 second of thought, yes, it can probably be done now with today's technology with AI. But advanced reasoning is something that we just don't know how to do yet.
So Ray, we've got a couple questions that are sort of in the same vein, and that is looking for some kind of sense of how you are defining intelligence. Are you talking about computation, or are you talking about something more?
So when I talk about intelligence, it is more than computation. Computation is more like a calculator, or what a specific, say, computers are very good at number crunching, or step-by-step algorithms following the code. So intelligence is more reasoning. Think of the way a human would step back and they would think about something and they would apply prior knowledge to a particular problem before coming up with a solution.
Okay, thank you.
Okay, so now we would ask ourselves, well, why is AI just becoming now so practical in these, why are we seeing it coming up in our day-to-day situations? Well, there's really a couple of reasons. The first one is availability of data. It's actually become quite popular. It's the in thing to collect these huge data sets, what do we call these huge supervised data sets where humans are collecting information and storing on computers. And then what we actually do is we train these computer algorithms to read in that particular data and be able to make inferences about new things that they've never seen before. We've also seen lots of sustained advances in hardware, especially GPUs, general processing units, as well as algorithm learning techniques. All computers, these omnipresent connectivity, the IoT, everything's connected to everything else. And also this lower cost and power consumption allows us to use even just like coin cell batteries to put sensors in all different parts of the world. So if you take a look on the right-hand side, what we have here is we have a plot, and that particular plot is just showing, say, the more data that you have on the x-axis, the better performance you're generally going to get. And so traditional machine learning techniques essentially would say, yeah, the more data you give it, the better it's going to perform. Well, over the past, say, 10 years or so, it's becoming, these algorithms are getting better and better, working smarter and smarter with hardware, in particular these GPUs. And now with these GPUs, we see, wow, we can get really good performance, and we could even get better performance on today's supercomputers. But keep in mind that today's supercomputers are tomorrow's cell phones or smartphones. So it's just this is just developing, evolving in front of us. So one of the hot trends today is that we have lots of high-performance architects teaming up with deep learning experts, and those are generating some of the highest, most demand jobs with the highest salaries. Now, if we take a look at some AI jobs, what I mean by this is that, well, in what aspects of life is AI really replacing humans? Well, they are already replacing humans in that, say, for credit cards. Who do we give credit to? Who do we not to? So for many years, we've been using computer algorithms to do this. Same thing with clerical tasks. If you think about ATMs, maybe we don't need bank tellers anymore. When you go up to, to the store, if you think about the automated checkout lines that you have in your local grocery store or your home improvement store, it's becoming more and more common to go to lines which don't need a cashier. Same thing with insurance claims. Even you think about litigation and lawyers, it's almost impossible for a human to read hundreds and hundreds of cases, thousands and thousands of cases, perhaps millions of cases, memorize all them, and then they hear your new particular unique lawsuit, and to make inferences and remember all those, say, tens of thousands of cases. Humans have a difficult time doing that, but computers are very good at doing that. Same thing with conversation bots, law enforcement, and in healthcare. We're seeing lots of influence from AI. Now, deep learning, which is what this particular webinar is about, is really the hottest topic in pattern recognition. And when I say pattern recognition, computer vision would mean the ability to look at visual stimulus and make inferences. In this particular example, this would be facial recognition. The same thing with speech recognition. We can process speech. Say for this particular webinar, it has to be captioned. There's automated captioning techniques which listen to what I'm saying and turn it into words. And then, yes, a human would, after the fact, come and look for errors today. But tomorrow, we won't need that post-processing check by humans. Same thing with security, medical diagnostic, and even financial trading and arbitrage. So here's an example. On the left-hand side, I'm showing an image which is a low-resolution image of some text, pretty difficult to read, but you apply some very straightforward deep learning techniques and you can get the image on the right, and it's so much easier to see. Another example, well, let's talk a little bit about computer vision. Well, so in this particular, say, task, you would give a computer an image and you say, what is it? And they would say, oh, that's a cat. Or you may say, okay, here's an image, find all the cats. And it would actually have, well, find all the objects. It would have to draw a bounding box around all the objects and then label all the objects appropriately. In this case, it would find one object, draw a bounding box around it, and say, hey, that particular object is a cat. And so you can extend this to doing multiple objects. And you could even extend this to say, hey, square bounding boxes, hey, that's so old school. That was like, a year or two ago. Technology is evolving so fast that now these latest deep learning techniques are saying, hey, I'll label every single pixel in that image, whether it's background, cat, dog, or duck in this particular case. So we could do both single and multiple object recognition. Take, for example, autonomous driving. So what we're seeing here is, so this is a dashboard cam from a car, from an autonomous car. This is the camera looking out, and you can see a couple of things happening here. First of all, there's one deep learning algorithm which is finding all the objects in the scene and labeling them. So for example, it's finding all the cars, and there's these magenta numbers on top of each one, and so that gives it a unique identity to each particular car. So one deep network, its only job is to find all the objects and track them over time. The next deep learning model generates these blue lines, and its job is to, hey, find the lane markers and identify the lane markers in the image that I'm seeing. And the third deep learning algorithm that's going on in this particular car is the red lines. And the red lines say, hey, what is my path now and into the future? So it's actually controlling the steering as it's going through. What I'm going to show here, this is a video. This is courtesy of NVIDIA, and it's showing an autonomous car going through the streets and identifying objects in real time as it's driving. And in particular, it's identifying people and cars and streetlights. And then now that even this technology is extended to identify every single pixel in that image. Is it the roadway, the sidewalk, is it the cars, is it street signs, is it people, is it motorcycles? And each of these objects has a different color. Now, not only has AI been influencing, say, specific technologies, but it's also good at doing things like art. For example, say you took this really awesome picture from Germany, and let's say maybe your favorite artist of all time is J.M.W. Turner. well, what would have that image that you took look like if J.M.W. Turner had painted it? Well, J.M.W. Turner is no longer alive with us, but using modern machine learning techniques, we can say, hey, we can mimic the brush strokes of J.M.W. Turner, and in the upper right-hand corner, that's what your photo would have looked like had J.M.W. Turner been alive and painted your photograph. Same thing, we're showing Vincent van Gogh and Edvard Munch on the bottom. And so, for example, you can change your profile pictures as if, well, what if Van Gogh were alive today and he painted your portrait? Well, now you can use that as your profile picture. Other examples, every single smartphone that's out on the market today has speech recognition, and each of those speech recognition uses deep learning. Image and video captioning, we've already seen how you can take an image or a frame and you can recognize all objects, but on the right-hand side, we're even showing, hey, you could take a picture or a frame or a video, and you can give it to the computer, and you can say, hey, what is going on in that frame or that picture or that video? And for example, it would kick out a group of people shopping in an outdoor market. Oh, that's interesting. It's never seen this picture before, and it generates that sentence. Then you say, tell me more. And it says, oh, there are many vegetables at the food stand. Keep in mind the computer's never seen this picture before. Now, there's been other studies showing that speech, especially the students, they love texting. They're so good at it, so much better than me. But now some new studies are coming out saying, hey, by the way, speech recognition is so good, it's up to 3 times faster to communicate with your friends using speech recognition than using, say, your clumsy thumbs, in my particular case. And they did the study in both English and Mandarin. I love these AI assistants, Google Home, Alexa. This is the new fad. Last year during Christmas, these things were selling like hotcakes, and I imagine this coming year they'll be one of the hottest selling products. So we're going to see more and more, OK Google, or Ask Siri questions, or Amazon Alexa. Different, they could be Wikipedia questions, they could be about your calendar, they could be about, giving you advice, this, that, and the other thing. All right, let's take a step back for a second and talk about the human brain, because the human brain is it's the marvel of the universe. The human brain is made up of what I call billions and billions of cells called neurons. Each one of these neurons is connected to up to, say, 10,000 other neurons, forming a vast, intricate connection, a web of connections, maybe 100 trillion connections. There's nothing like that we know in the universe today. It's really such a marvelous universe, and we've done so much studying on it. As a matter of fact, we've learned more about the brain in the last 5 years than we've done in all prior years, yet we still know very little. We have no idea. How does this brain store, say, all my memories? I can remember when I was 4 years old sitting on a stool and my parents were saying happy birthday. How do I remember that? How do I have the ability to have emotion, the ability to love and to hate, anger, or to learn new concepts or to generalize? It's just amazing. Well, if you take an example like this, what we have here is there's 30 images on the left-hand side, each of 4 different classes: airplane, cat, car, and dog. And because you as a listener have one of these awesome Marvel universes in your head, because you have a brain, you can look at any one of these little images and you can classify it as one of these 4 classes, yet they're all so different. If you look at all the cars, they're completely different from one another. How is it done? Well, the one thing we do know is that there's many layers of an abstract hierarchy in the human brain, where, say, the V1 of the visual cortex of the eye brain has what we call these Gabor filters, which are just, say, dampened sinusoids, Gaussian dampened sinusoids. Those form building blocks into what we call V2 of the visual cortex, which form, say, simple corners and edges, which form building blocks to V3, which turn those corners and edges into parts of objects, which feed into V4, which turns them into, say, objects themselves, and so on. Well, so your brain is so good that you can tell that all these images are cats despite changes in deformation. You can tell all these images are cats despite the occlusion that we're seeing here. You can tell that all these images are the same cat. This is Tartarsaurus, a grumpy cat. It's a famous cat on the web. But they all look the same. You can recognize them as all the same cat. And you can recognize this picture as having a cat despite the background clutter. And finally, you can easily detect that all these objects in this particular scene are cats despite their huge class variation. Okay, so what we want to do is we want to somehow teach computers to see. How do we do that? Well, all right, so evolution, maybe since, the amoeba 500 million years or so, well, somehow the eye brain has developed over those years. Let's say the modern child, in today's era, let's say this particular child that we're seeing here, let's say that he collects a new image every 200 milliseconds. By age 3, this child will have processed over 200 million images or 200 million training samples. If you actually do the math, which is that computation over there, it's actually like 236 million. So, but it took that child's brain, say, 3 years to process and learn those 236 million images. With modern day computers, we can do that in just a few days. And that's why we're able to teach such amazing things to computers. Now, so the idea is that traditional machine learning and computer vision was really built off of, smart engineers in the lab saying, hey, I think I know what is making me be able to tell the difference between a cat and a dog and a motorcycle and a boat and so on. And we would code up these, these gut feels, these cues to help the machine learning generalize. Well, what we do today, though, in deep learning is that we say, hey, we finally realize that computers are better at coming up with those cues than humans are. So we just feed all the information, and in terms of computer vision, all the pixels of the computer, and we say, hey, you go ahead, you try to figure out what the good features are. All right, so what I want to do is I'm going to spend a couple of minutes talking about what we call an artificial neuron. So we have biological neurons in the human brain, and we're sort of going to loosely mimic them in what we call an artificial neuron. And what we see here is that what an artificial neuron will do, just like a biological neuron, it will just take a weighted linear summation of a whole bunch of inputs, and then it will pass it out. There's a couple different representations you see here, and in the bottommost one, we're just showing a very simple mathematical representation, which is just a dot product. But what is interesting is that this G function is what we call a nonlinear activation function, and that nonlinear activation function mimics sort of what happens in the human brain, where we can pass this weighted linear input summation through some nonlinear activation function, and then take that output and pass it on to many other neurons. Now, if we take a whole bunch of those artificial neurons and gang them together, as seen on this particular slide, we form what we call an artificial neural network. And when you start taking, say, hundreds of thousands of these and ganging them together, intelligence starts to emerge. And this is very similar to the way we think that maybe this is how intelligence emerges from the human brain. So what we have in this particular slide is, I'll give you an example of how something like this may work. We would take an input stimulus, and in this case, we'll use vision as an example. And let's say we have input images which they'll be low resolution. Say they're 20 by 20 pixel images. So 20 by 20, that's 400. So let's say we have 400 inputs to our neural network. Each input would be one of those pixels. What we do is we take that input and we pass it into our neural network, and each neuron, remember, is a linear combination of the inputs, and then it takes that output and passes an output to the next layer. Ultimately, what we're hoping for is when we get to the very last layer, because this particular image was a human, we'd like to say the red dot, which corresponds to humans, should light up. The rest of them should stay dark. And what we mean in computer lingo is, well, we hope that the red dot, which is the third one down on the very most right-hand side, is for humans. We hope that one is, say, a high value, and we hope all the others are low values. And in this particular neural network, it says we have C different classes. So that means this particular neural network is capable of recognizing C different types of objects. Only one of those is people, so we'd want the people neuron in the output to be hot, and the rest of them say 0. Well, initially when we compare it to the ground truth, we'll see that we have some errors. And so the green dots on the right-hand side represent the ground truth answer. So for this particular input stimulus, which is a person, those green dots would all be zeros, except for the third green dot down, which is meant for humans or pedestrians, and that one would be, say, high. And so we're going to have error. It's not going to do a good job initially. And so what we do is we propagate that error backwards, updating all the weights in that particular network. And then we take a second stimulus and repeat the whole thing again. And then a third stimulus, and a fourth stimulus, and maybe 100,000, maybe 1 million different samples, each time fine-tuning and adjusting these weights. And then we'd repeat that whole process again over and over and over again. Each time we go through each sample on our training set, we call that one epoch. And we use something called back propagation to update that. And I'm not going to get into the details of that in this particular.
Oh, great. Let's just take 1 second because I think our second poll question is up. So if people want to weigh in on what Ray was just talking about with regard to the artificial neural networks and their similarities to human brains, go ahead and take a few moments and read those responses. And I think this is one where there's multiple answers that are possible.
Yes.
Is that correct?
You can check more than one answer.
So you can pick more than one answer. And in the interim, we do have one question that was asked, and that was, do you believe that machines will be able to develop, I'm sorry, now let me read it again. Do you think it's possible for machines to have something like emotional intelligence?
Yeah, well, that's the long-term goal. That's where we're going. Certainly machines do not have the ability to do that today. We have something called effective computing, which is the ability of machines to, say, direct or steer human emotion, and certainly we're getting very good at that. A machine, for example, can look at your face, it can find all the features in your face, and it can make pretty accurate guesses about your mood, if you're happy or sad or angry, for example.
And they are actually working on that here at RIT in the School for Behavioral Health.
Yeah.
As methods of treating and working with people with mental health issues. Is that correct?
Yeah, especially we call these things so micro-expressions. Machines are better at detecting these micro-expressions than humans themselves. So there's no question that a machine will be able to detect your emotion, or perhaps if you're lying or not, better than a human will be able to do. And some machines are arguably better than humans at that already today.
Okay, and one other question was with regard to the self-driving cars and the sensing of that. Can you pull those questions up there? Great. So there's two similar questions. How do you think having automation across civil society, such as self-driving cars, will be regulated? And can a self-driving car be prosecuted? What are the ramifications from the law enforcement perspective?
Yeah, so right now that's probably the biggest impediment to autonomous driving is legal ramifications, and that's being settled out right now. Ironically, New York State is the only state in the union which doesn't allow a car. You have to have at least one hand on the wheel at all particular times. Other states are much more free about that. For example, states like Nevada and California, for example, allow autonomous driving, as long as there is a human driver in the car who is able to take over at any point in time. So as we learn, as we get more experience, we're going to come, and I think in the very near future, when I say that, I mean within the next 10 years, we're going to be in this state where machines are so much better than humans at driving that there's going to be a very quick switch where all of a sudden it's going to be like, wow, why would you ever drive that car yourself when a machine is so much safer at doing it than you are? And when that happens, that's when we're going to have very swift legislation, and that's when most of these laws will be enacted.
All right. Do we have our poll question answers?
Yes, we do, yeah.
Okay. So you can see that. Oh, are we able to open that a little bit? Yeah. So they both have similar. I'm sorry, bear with us, folks. We're trying to open up the screen so we can read those questions. They both have the concept of neurons, which produced a weighted sum of inputs. That was selected to a large degree. A little less was that they are both nonlinear in nature. Several people selected that they're both hierarchical in nature and learn abstract representations of objects. No one liked that they both have similar number of connections.
So the first two were true. And the second two, I would say, well, the last one definitely is not true, because you can have 100 trillion connections in the human brain, and modern deep neural networks may only have a couple 100 million networks inside them. So I guess the issue is that the hierarchical is something which is subjective. For a traditional neural network, there is no sense of hierarchy like we have in the visual cortex. The reason I put that in there, though, is when we talk about deep learning, there definitely is this notion of a hierarchical abstraction where we have, say, first these Gabor filters, then edges, then parts of objects, then the objects themselves. And this is one of the key things which separates deep learning from traditional multi-layer perceptrons, which we've seen so far. So what we'll do next is, let's just take a quick look at what we call these convolution neural networks. This is probably the most famous of all the deep learning networks. And let's see if we can see how those work. So first of all, so this is a picture of a convolution neural network. This was circa 1980. And if you just take a look at this, you don't understand what it means yet, but it essentially takes some input and it has many layers, and then there's some sort of classifier at the output. If you take a look at the CNNs today, they're all very inspired by some of these, futuristic thinkings of the, 1980s. So there really, you could say there hasn't been too much going on there, but, as you'll see shortly, revolution in the past 5 years has really been all the learning, is all the discovery in deep learning. If you can contrast deep learning with traditional learning was really centered around coming up with what we call these human handcrafted features, and then using those human handcrafted features in conjunction with independent learning algorithms like support vector machines, neural networks, say sparse representations, and then doing some sort of image or audio or pattern recognition on top of that. In contrast with deep neural networks, we're going to have the deep neural network do all that itself. It's going to come up with the best features to extract, and it's going to learn the best classifier, and it's going to learn both of them simultaneously. And the reason we couldn't do this, say, in 1980 or 1990s or even 10 years ago was because we just didn't have enough computational power. Today, not only do we have enough computational power, the other thing that these deep neural networks need is lots of training samples. And now, with the sharing of data, we have those lots of training samples. You got to figure, if you have 100 million weights you're trying to solve for, man, you must need at least 100 million training samples to solve for those 100 million weights. Well, not exactly, and so there's some shortcuts that we use to get around that. So this is just showing, so GPUs, the quote in the upper right is interesting. In 2016, a single high-end NVIDIA video card for a gaming PC would have been classified as the most powerful supercomputer in the world before the year 2002. And since 2016, the technology has again gotten twice as fast. The GPUs which were released just last month are twice as fast as the ones in 2016. Now, convolution filters, or the deep learning, is really predicated on this concept of convolution filters. And when I say convolution filters, I'm talking about the same exact filters that you may have learned in signal processing, where I'm showing a simple convolution filter or a vertical edge detection filter in the top, and that job of that filter is to find all the vertical edges in the scene. And so we're going to use that same concept in CNNs, and what's going to happen is the CNNs, or the convolution neural networks, are going to learn which of those convolution filters are good for feature extraction. And so that's sort of shown by the nine filters on the right-hand side of this particular slide. Those 9 filters will take the original input image and create, say, 9 filtered versions of those images. And then what we'll do is we'll resample those 9 to a lower resolution and repeat the process such that we get a hierarchy of images. And so that's what we're showing over here. So now this is that first diagram we saw. So this was actually published in 1998, although the original concepts were 10 years or so earlier. So it takes an original image, it learns some filters, it filters those images, and now we have filtered versions of those images, and then we learn more filters on top of that, and we create more filtered images, and eventually these, where it says C5 to F6 to output, those stripes, those sort of like slanted vertical stripes, that's what we call these fully connected layers, and that's sort of analogous to a support vector machine, for lack of a better analogy. And so the idea is one stage of a convolutional neural network would take some input, do the convolution, followed by that pooling, where the convolution is the filtering operation, the pooling is the resampling operation. And what we're going to do is we're going to repeat that step multiple times and then have those fully connected layers, which are analogous to the classifier at the end of it. And each of those is weights that we're going to be learning. And so the idea is that specifically, and here's an image which is 28 by 28 pixels, and maybe we'll learn 5 by 5 filters, which are across the top. And so since we're learning 32 filters, we'll get 32 filtered images, which are shown to the right. And you could do the same thing for color. The only difference now is that the filters, instead of being 5 by 5 by 1, now they're just 5 by 5 by 3. But we still get 32 filters. All right, and so the other concept is pooling, and the pooling allows you to have some sort of freedom or invariance to exact location of an object, and it also gives you that notion of an abstract hierarchy. And the most popular method used in deep learning today is something very similar, and that's why I'm showing it. It's called max pooling, where how do you reduce the image on the left, which is 4 by 4 pixels, to the image on the right, which is just 2 by 2, or you split it up into regions, and you just take the maximum pixel value in each region.
So let's pull up our last polling question if people want to take a look at that and give us your thoughts. We do have one question also while the polling question is up, and that is that much of this seems to be centered around images and visual stimuli. Are you familiar with any developments using other senses like sound or touch?
The only reason we use visual stimuli because it's very easy for humans to relate to. We see something, we can relate to it. But everything we're doing here, it doesn't matter the input modality, whether it's sound or touch or audio samples, whether it's some signatures from the stock market or signatures we're getting from different sensors on your body or medical images. It doesn't matter. The deep learning techniques still would use an abstract representation and still would pair it with a classifier at the end.
Okay. All right, so if people want to keep finishing up that poll question, it looks like we're just about done. How are deep neural networks similar to traditional networks? Or I'm sorry, how are they different from traditional networks?
Well,
oh, go ahead.
So the first one is they use convolution filters to learn spatially invariant features. Well, certainly yes, convolution filters do that, but traditional neural networks do not do that.
We had not much, just more layers?
Yeah, so really I would say that's sort of true because they are more layers, but instead of what we call fully connected connections, we're using these convolution filters between each. And so is that a subtlety? One can argue back and forth. So yeah, so that more layers is probably the biggest differentiator between the two.
And then your third option was they simultaneously learn features and classifiers?
Yeah, so these deep neural networks, this is why the other machine learning techniques can compete with deep learning techniques. And I'll throw traditional neural networks into the traditional machine learning classifiers. How can you compete with something which is optimal learning, feature extraction, and classifier at the same time? And so this gives an edge to deep neural networks. Just give you a quick visualization. So what we're looking at over here, this is a multi-layer deep neural network. And in layer one is learning these filters, which are akin to what I call those Gabor filters, which is those dampened sinusoids. And so the gray shows the filters themselves, and then the colors is portions of images which are triggered by those particular filters. Then if you go to layer two, you would say, oh, okay, so now what I'm looking at is I'm doing a visualization of the type of things that the second layer triggers on. And you can see that the second layer is now triggering on fancier edges and very simple concepts. Where if you go to further down layers in the neural network, say to layer 4 and layer 5, in layer 4 we're clearly starting to identify parts of objects. And in layer 5, those filters are clearly starting to identify those objects themselves. And by the way, we don't tell the network to do that. It just automatically does it itself. Now, these things are so good that virtually deep neural networks are winning all the computer vision, all the pattern recognition challenges, virtually all of them that are out there, whether it's handwriting recognition, whether it's image classification, or simple things like traffic sign recognition. They're better than humans in all these particular cases. I'll just take one case study, which is something called ImageNet, and this is a computer vision challenge. And the idea is that you want to recognize different objects. And there's 1,000 different types of objects that you would have to recognize. Well, unless you think that these are simple object categories, here's one of those categories called hammers. And you can see all the different variations of hammers that we're asking this network to learn. Each one of these, whenever it sees one of these images, it has to say, oh, there's a hammer in there. Wow, and these are hard. Many of these, even me as a human, I've never seen hammers that look like this. Yet, the computer is able to recognize all these as a hammer. And so if we take a look at how computers have done over the past couple of years on tasks like this 1,000-class computer vision object recognition challenge, you see that in 2010, 2011, if we look at the error, those errors were, in the 20s. Well, in 2012, that was the introduction of deep learning. And so we had over a 30% reduction in error by introducing deep learning. Wow, that took the machine learning community by storm. And in 2013, so only one method used deep learning in 2012. In 2013, all methods except for 2 entries used deep learning. And in 2014 and beyond, now only deep learning techniques are used for computer vision challenges, which are as difficult as this. Now, you would think that, okay, well, how do humans stack up to these machines? Well, there's a guy named Andrej Karpathy from Stanford fame, and he's what I would call a genius intellect, one of the smartest guys on the planet, at least with regards to artificial intelligence, and he trained himself on this challenge. And he said, hey, look, I can get about a 5% error, so I'm still better than humans. Well, within a month of him publishing his results, Google and Baidu both came out with results which were on par with his and said, oh, see, now computers are just as good as you are. And, well, all right, in 2016, computers now cut his results in half, and so now we can say unequivocally computers are better than humans at difficult tasks such as this. Okay, so I think I'm going to have to wrap things up due to time, but I just want to say one thing about artificial intelligence versus intelligent augmentation. Right now, okay, so artificial intelligence, that's really giving, computers the ability, remember one of you mentioned intelligence, emotion, ability to think and reason, to independently act on its own. So we'll call that artificial intelligence. Today, what we're really seeing, even with these fancy deep learning models, is what we call intelligent augmentation. This is doing simple tasks, but each of these simple tasks is making our life better, faster, easier, more efficient. Now, both artificial intelligence and intelligent augmentation are hot topics. They're really driving many startup companies. Here's some examples in this slide of the difference. I'll just cover one of them, which is, say, enterprise. Well, intelligent augmentation would be the ability to automate, say, mundane tasks. In other words, like automated tellers or something like that, virtual assistants. Where artificial intelligence is, oh, now you have machines which do all those tasks themselves without any assistance by a human, and they can do it better than humans. Now, here's a quote. An engineer often overestimates what she can do in 5 years and underestimates what she can do in 20 years. And I think in my career, this is often true when I look back at when I was making predictions. And we see 2 different curves on this plot. One is the intelligent augmentation, and the other one is the artificial intelligence. Most people think we're, riding this, steep increase in technology and artificial intelligence, when really we're only on this intelligent augmentation curve. We're really just starting the artificial intelligence, and it really will be many years from now before we start seeing agents just as smart as us interacting with us in our everyday environments. All right, so I'd just like to conclude and say thank you very much, and I wish you all the best.
Perfect. Thank you very much. We've got, I'm going to take one question, and then we'll jump into our closing. The question, I think, is that is there any core issues with DNN that's currently holding it back? example, the amount of data needed for training or sensory transformation.
Well, so Craig, I believe this is from you. So ironically, you in your garage or your basement can buy an NVIDIA GPU for less than $1,000 and pair that up with a desktop computer for, say, maybe $1,200. So for about $2,000, a little over $2,000, you can generate you can create a piece of hardware, and then you can download software, which the smartest companies in the world are using. You can download the identical software to what they're using. And your, say, over $2,000 computer can start competing with those supercomputers that, say, Google and Baidu and Facebook and Microsoft are using. So really, we've reached this age where computing power is getting so cheap and so ubiquitous that is probably not holding us back right now. I think we're getting very good at these supervised techniques, and we're about peaked in capability. To get to this new level, to get away from intelligent augmentation and towards true artificial intelligence, we need new invention to happen. And so if you're going to ask me what essentially is that, we don't know. Just like, 50 years ago, we would have never envisioned people walking down the streets, everybody's looking at smartphones and texting, and are you kidding? They're doing live video chats wirelessly from people around the world? No way, that's not going to happen. It's probably what we would have said 50 years ago. So right now we don't know, what is that new break in technology that's going to happen. But I'm more on the side of, I think within the next 40 years or so, we'll probably see machines which are smarter than humans, and they'll be pretty common.
Okay, well that is all the time that we have. If you have additional questions, you can email them to ritalum@rit.edu or tweeted to @RIT_alumni with the hashtag #MeRITWebinars, and we'll direct your questions to Ray. Ray has also left his email up there on the closed slide, and you can find him at the Machine Intelligence Lab at RIT. So we thank Dr. Ptucha for being our panelist today, and thank you to all of our listeners. Please consider joining us on June 28th for the very last MeRIT webinar of this academic year, when we will offer a provocative presentation, 10 countries that don't want to defeat ISIS. Our presenter will be Robert Gerais, an adjunct professor in RIT's Environmental Management and Safety Department, and a 27-year veteran as a Naval Reserve Intelligence Officer in support of the Defense Intelligence Agency. Again, you will receive an email with a link to the recording for this webinar in a few days, and I believe we will also attach Dr. Ptucha's slides to that email so that you can view the slides in more detail, and if you have further questions, we'll certainly field those. Thank you all again for joining us. Please exit the webinar by simply closing the WebEx window, and please do let us know what you thought of the webinar through a brief survey, which will pop up when you exit. Have a great day.